All right, so once again, we want to obtain the power series of some unknown function from the power series of a known function. And we want to do this by integrating power series. So let's see how that actually works. So the idea is that we are given a power series expansion of a function, so f of x, and that power series has a radius of convergence of r. Well, in the case that the function is differentiable in that interval for which a power series converges, then we can differentiate the power series term by term and obtain a power series expansion of the derivative of the function. And likewise, if we integrate the power series term by term, then that in turn gives us a power series representation of the integral of our original function f of x. And in each one of these cases, the radius of convergence in the differentiation and integration case remain exactly the same as they were for our original function f. So let's apply that in this case. So here we know we have for our geometric power series that it has a representation from n going from 0 up to infinity, so 1 over 1 minus x, it gives us our power series x to the n. And further, we know that that was going to be valid for the absolute value of x less than 1. Well, just doing a substitution, then we obtain the power series for 1 plus x, by just doing a substitution, n equals 0 up to infinity for minus x to the n, which gives us then a power series, n equals 0 up to infinity for minus 1 to the n, x to the n. And so what our theorem just told us was that if we do the integral of 1 over 1 plus x dx, then that gives us, to an arbitrary constant, some sum n equals 0 up to infinity as if we integrated our power series term by term dx. And so what happened in this case, so now if we do that integration, what we obtain, so if we do that power series expansion, we can pull that negative 1 to the outside because it's just a constant not depending on x. And so we end up with c plus the sum n equals 0 up to infinity of minus 1 to the n, then just using the power rule, 1 over n plus 1, x to the n plus 1. And so if we integrate both sides, so now integrating the left-hand side, we just have the natural log of the absolute value of 1 plus x equal to c plus that value, c plus this infinite series. So now comes the question of what exactly is c? Well, remember that our power series is still valid in our integral for the absolute value of x less than 1. So if we plug in 0 to both sides, what happens if I have the absolute value of 1 plus 0 over on the left, then I also get c plus our sum n equals 0 up to infinity for minus 1 to the n over n plus 1, 0 to the n plus 1. Well, these guys are all 0, and so that whole power series is just 0. And so on the left-hand side, I have the natural log of 1 is c, or c is just going to be 0. And so what happens, I have the power series expansion for natural log of 1 plus x just being the series n equals 0 up to infinity minus 1 to the n over n plus 1 times x to the n plus 1. So now coming back and looking at the function which I really wanted to evaluate, I want the power series expansion, so I want 2 times the natural log of 2 plus 2x minus 2 natural log of 2. And so what happens in this case? Well, I could factor out that 2, natural log of 2 times 1 plus x, minus 2 times the natural log of 2. And so what happens, then I could use my properties of logs to say that that's going to be the natural log of 2 plus the natural log of 1 plus x. minus 2 natural log of 2. And so what happens if I distribute my 2's? I have 2 natural log of 2 plus 2 times the natural log of 1 plus x minus 2 natural log of 2. And so my 2 natural logs of 2 cancel out, and this is really 2 times the natural log of 1 plus x, but I know what that power series is. I just did it. So that one is going to be my sum, n equals 0 to infinity of minus 1 to the n over n plus 1, x to the n plus 1 power, and all of that multiplied by 2. So I actually have a power series expansion, 0 up to infinity, 2 times minus 1 to the n over n plus 1, x to the n plus 1. And so if I want to write out the first 4 non-zero terms of that series, what will it look like? So just taking that series, plugging in values for n to see what happens. So when n is 0, I get a 2 over 1 x to the first power minus 2 over 2 x squared plus a 2 over 3 x cubed and a minus 2 over 4 x to the fourth plus 2 over 5 x to the fifth, and so on and so on and so on. And so our first 4 non-zero terms in our series are actually 2x minus x squared plus a 2/3 x cubed minus a 1/2 x to the fourth plus bada bada bada. And so we have our power series expansion for our function, and we could approximate that with the first 4 terms of that series. So I hope you've enjoyed this, and I will see you guys in the next one.